Welcome back to the lab. In a previous video I showed you an API discrete component microphone preamp that used both input and output transformers. Today I'm going to be showing you a different type of preamp that does not use input and output transformers. The preamp of today's choice is going to be a OPA 604. This preamp has been used in professional audio equipment, digital to analog converters, active filter. This preamp also has a very low distortion of a 0.003% at 1 kilohertz total harmonic distortion. It also have a very low noise floor of 10 nanovolts. It also has a high slew rate of 25 volts per microsecond. Also has a very wide bandwidth, 20 megahertz. The power supply range is very wide, from a 4.5 volts to a 24 plus volt and minus. It also can handle a very low impedance of 600 ohms, which is very suitable for audio, and that's why this preamp is a preamp of choice today. Now I'm going to start by wiring up the preamp. With all discrete component op amp, or all op amps carry both a inverting and a non-inverting side. So I'm going to start by hooking up the two inputs of the preamp. These type of preamp costs a lot less to build because of the fact that you're not using input and output transformers. Those transformers and those preamp can drive up the cost a lot. These type of preamps is used in your everyday console all the way to SSL, and even a lot of digital consoles use these type of IC microphone preamps. They cost a way lot less because you do have to put each channel with input and output transformers, which keep down the cost a lot. The next section I'm going to be wiring up is going to be the phase switch. This is a switch that you would push on the microphone preamp or the console if a signal was out of phase. It has all the same features like phase, pad, phantom power. had extracted these parts before and already worked out the maths to save us time going looking for the parts in the parts bin and installing them. We save a lot of time this way. This is where we're gonna have our 48 volts come in. Gonna change the value of these resistors to 100 key. So when this get 48 volts, the microphone get the phantom power, and then this stops the amplifier from receiving DC. This section of the amplifier is what maintained a balanced input. This section of the amplifier is what controls the buffer stage, the output stage. It controls gain. I'm going to install this feedback resistor. The feedback resistor is what we use to control the volume or the gain of the amplifier. The higher the higher the value, the higher the value is the more the gain. If I was to change this from a 10K to like a 47K, it would put out more gain. Almost finished. oscilloscope. And the oscilloscope is what monitors the different area of the circuit. And the D side of the scope is going to be monitoring the output of the preamp. Okay, so we got everything here going. Let me install a dB meter. Then this side to ground. And we're selecting decibels, AC. Okay, let's flip the switch and see what happens. Change the time base. Change the voltage. So I'll AC. Let's see how low I'm coming in. Okay, 100 volts. So let's take this down at the input to about 100 millivolts so we could see. So both the A side and the B side is on the scope, it's set to 100 millivolts because the input is only coming in at 115 millivolts. And this is all AC, and the D side of the scope, which is the output, is set to a 2-volt scale. So as you can see here, it's perfectly lined up with input and output. Let's see how far up I can go with this preamp. Well, I'm over the 2-volt scale, over the 5-volt scale. I'm on the 10-volt scale, and it's clipping. could see where the red line is inverted. If I go back the next way, it's not out of phase. So this is what the phase switch does. Alright, now it's in phase, and if something was out of phase, it would flip it back in phase. So in phase and out of phase, you notice the direction of the line, that where the line's going. If you look at it, see you have the positive cycle. Then this didn't come. This cycle was not a positive cycle. It went to a negative cycle. And when this go to a positive cycle, this is a negative cycle. They're not moving at the same time because it's out of phase. Look what happens when I press a switch here. Notice the switch move. It goes in phase. Let's test the frequency response of this preamp. I want to use a blood powder to test the frequency response. And with any audio design amplifier that you're doing, they have to be able to pass from 20 to 20,000 cycle. That's what the audio spectrum is made up of. And before you even listen to an amplifier, you can tell with this tool if it's going to pass the frequency response test without even listening to the amplifier. What we're trying to do is to get a straight line. So let's see what we get here. Okay, I'm set to the gigahertz to 1 gigahertz. So I'm going to come down, let's say 1 megahertz, so I can get a more accurate reading. And this is below hertz, millihertz. I know a lot of people probably don't believe it exists, but yes, for testing purposes it does. So right now I'm at 50 millihertz. Let me go to 1 hertz. And this is for testing the efficiency. So if I let me do 500K and see. So at 500K, I'm pretty much flat, which is what we're looking for. So we pretty much have a flat response. Let's see what the roll off is. See, the roll off start at 4 hertz. And let's see if we can adjust the scale here at 50K. See, it's still going on above 50K. So by installing this capacitor across the feedback, we should see it start to roll off above 20, because we want to really get it to roll off above 20. The amplifier that we're using, based on the data, it shows that it can go up to, I think they said, 25 megahertz. But that is if you're dealing with a RF or a cell phone. We're in the audio band, so we're not there. So as you can see here, it rolled off after we install the capacitor. You see, we start to get it after 19, 20. Now it started rolling off after 21, which is what we want. Now the preamp is done. It checked out well. One more test. One more test. Let's test the distortion rate. Distortion analyzer. Remember, the data said what? It had a very low distortion rate. Let me go back and see. The data set as a 0.003 at 1K total harmonic distortion. So let's see when we fire up ours, what the distortion is going to come out at. Wow, I got it to go on to wow, look at that. Look at that. Um, all zeros, all zeros, and that's at 19 dB. Let's put a load on it. Let's put a load on it and see what we ends up with. Let's put a 10K load. So a 10K load is a point zero. It still went back to no distortion even with a 10K ohm load. Let's go down and how clean is it? It's still no clipping. Let's go down to a 1K load and see what happens at 1K. See, in the real world, when I was building this, I would have to unsolder that 10K resistor, either go buy a 10K resistor or put one in, which take about 5 to 10 minutes, and I would test it, and now it's still showing me no distortion. Um, Even at 10K, let me go down to a 600 ohm load as they recommended. 604. Let's see. All right. Wow. This is really a good op amp. Let me see what this looks like on the square wave pattern. You'll notice the distortion go up at square wave, but that's not what I'm really looking for. I'm looking to see if I get a perfect square wave. See, as you can see, the square, even at square wave, it's perfect. It's not overshoot or ringing. So, yes, you'll see this with square wave. Let's look at triangle wave. And it's expected at triangle wave to do that. Let's look at sine wave. Has almost no distortion. So now I'm going to build the printed circuit board for this op amp. So now it imported all the parts. So the first move is to pretty much put all the critical parts where you want to put them and lock it. So these right here are the critical parts. I'll put this here and I'm going to space it out a little bit. Going to adjust the size of the board. all these critical parts that I don't want moving, and I'm going to tell the program to find the best place to put these parts. So the program think here the best place to put the parts, and I'm going to route it. Now it finished routing the parts. Let me just change these two to XLRs. This one, place part, and I'm looking for XLR connector. Let me move these out the way and put them somewhere more. Again, okay, the board need to be a little bigger so it can figure out where to put the parts. So I ought to place it again. Still need a bigger board. So now I'm going to route the board. The board auto routed, and this is the microphone preamp. I'm going to look at it in a 3D view. This is it right here. Thanks for watching. Bye bye.